This week, we will learn the generalized linear models. Generalized linear model is extension of the simple linear regression model. Generalized linear model allows us to model some nonlinear relationship between the dependent variable and the independent variables. Generally, this model will try to change the structure for the linear regression model in the independent variable parts and try to transfer the independent variable, make it ready for use in the linear regression model. Before we learn the generalized linear model, let's record the simple linear regression model. For the simple linear regression model, we have two variables, the dependent variable, independent variable. In most of the cases, we will use a y to represent the dependent variable, use x to represent the independent variable. Dependent variable is this variable we try to explain and we try to predict. Independent variable is this variable we can use to make a prediction and we can use to explain the dependent variable. So here I show this formula. This formula we have the dependent variable on the left side of this equation, and on the right side we have the independent variable. So based on this data set, we can estimate the parameters for this variable. We can estimate the beta 0, beta 1. You may notice in this formula we have the error term. Those error term, it's normal distributed with a mean 0 and variance sigma square. After we get the data sets, we try to predict or try to estimate those parameters. How we do this? We minimize the sum of the square errors. For the error term, we only need to know the sigma square because we have some mean equal to 0. Once we estimate the parameters for this model, so we have the equation with all those parameters. After we get a new observation, so we can put the new observation into the system to make a prediction for the corresponding variable y. As I mentioned before in the last week, so the simple linear regression has three functions: prediction and the explanatory function, and also try to find the outlines for this system. For the prediction, so as I mentioned before, after we got a new observation, we can put this observation into the system to make a prediction for the corresponding variable y. For the explanatory function, which means after we get those parameters, we have the coefficients, so we can say whether the coefficients are significant or not. We can run the t-test to check whether the t for the beta 0 and beta 1 significant or not. So we can use the magnitude of the relationship sign in the beta 1 to see the relationship between the y variable and the x variable. We can see if there is a relationship on whether this relationship is strong or not, because we also know the sign of the beta 1, so which means we can know how those variables correlated with each other, connected with each other. If it's negative, which means the opposite side connected with each other. Before we use a simple linear regression, we need to make sure that those variables they satisfy certain assumptions. Here I show those four assumptions. The first assumption, we need to make sure the two variables, the independent variable and dependent variable, they are linear. They have the linear relationship. That's why we use the scatter plots to see whether those variables they have the linear relationship. And second, the assumption is we need to make sure those observations in this data sets are independent with each other. If we have several observations, they are dependent with each other, which means we can use one observation to represent all the other related observations. If we use those related or we use those dependent observations, those models will driven by those observations. So that's why we need to make sure those observations are dependent of each other. Third assumption is we need to make sure that the error term is normally distributed around the regression line. And the fourth one is we need to make sure the variance, the sigma square, is the same for all the value x. It cannot be increased when the value of x increases. After we make sure those four assumptions, we can use a simple linear regression. After we discuss a simple linear regression, we are ready to discuss a multiple linear regression. In the multiple linear regression, we have several independent variables. We just have one dependent variable. This variable we try to make a predict, and this is the variable we try to explain. So you can see on the right side of the question, we have the independent variable. We have independent variable x, we have independent variable x1, x2, x3, etc. So right side is a linear compilation of the independent variables. We have more variables, we have more parameters. We still have one error term. This error term will try to capture those hidden variables which are not shown in this multilinear regression. And those hidden variables will driving or will influence the value of the dependent variable. That's why it calls the error term. For the error term, it's normal distributed with a mean value 0 and the variance sigma square. If we try to estimate those parameters, we use the same method we used in the simple linear regression. We try to minimize the sum of the square errors. Before we do the multiple linear regression, we need to consider the assumption, the one more assumption. This assumption is that we try to make sure those variables, those independent variables, x1, x2, x3, x4, etc., xk, they are not highly linear correlated, which means any two variables from those independent variables are required not highly correlated. So this assumption we call it multi-collinearity. Why we have this assumption? Think about if right now we have two independent variables, x1, x2, they are linear correlated with each other, which means we can use the independent variable x2 to represent the independent variable x1. While we still include those two variables here, we just can use one variable to represent another variable, and we can reduce the number of the independent variables in the system. After we discuss the multiple linear regression, let's take a look at the dependent variable in a linear regression. Suppose right now we already have the simple linear regression. We know their parameters. We know the beta 0, beta 1, and we know the sigma square for the error term. Suppose right now we have a new observation and we want to get the possible value y based on the new observation x. We can put the value of the x into the formula so we can get value y. So in this formula, we can separate it into two parts. The first part we call it the non-random part of this equation. It includes the beta 0 plus the beta 1 multiple x. So this value will be a fixed value if we know the independent variable x. Another part of the equation is we call it random part. It's error term, which means we do not know its exact value. We just know the possible value for this variable. It will be in a certain range. So if we fix the value of the x equal to 0, we fix the value x on a0. So the value of y will be centered. Let's see this picture. It will be centered around the cross value. The cross value will be the regression line and the straight line between when the x equal to 0 will be here. Okay. You may see the value of the y. The value of y is spread, is normal distributed around the cross value. So you can see there is a normal curve, which is corresponding to the error term. So when we include the error term in this equation, it's driving the dependent variable as a random variable when we fix the value x. And the distribution of the variable y is normal distribution with a mean value equal to the cross value if we fix the value of x equal to 0. Okay, so the mean value will be here, cross value, and it will be equal to the beta 0 plus beta 1 multiple x. Let's try to sum up. So in the regression model, if we fix the value of x, the value y is a random variable that's normally distributed. So that's why when we make a prediction, we do not include the error term. We only use the two parameters beta 0, beta 1, and use those beta 0 multiple beta 1, beta 0 plus beta 1 multiple the value of the independent variable x to get the dependent variable. Because we can get the mean value. So we do not include the error item, which is a random part for this equation. And the beta 0 multiple beta 1 multiple x is the mean of the y. So you can see this one. So based on the value of x, we can predict the mean of the y. It's a reasonable value. As we discussed in the second lecture, and the mean is really close to the true value. In most cases, the mean of the y is close to the true value of y. It's a normal curve of the y is normal distributed when we have the fixed value. Here I show the alternative formula for the linear regression. So previously we have this formula. It includes the parameter 0, parameter 1, and the error term. This error term is normal distributed with a mean 0 and a variance sigma square. But right now we can use another one because it's the equivalent formula. In this formula we don't have the error term, and we use the mean of the y. the mean of the y will equal to the beta 0 plus beta 1 multiple x. And the y is normal distributed with this mean and the standard deviation sigma squared. Simple linear regression is very useful when we try to predict and explain some continuous variable that can take both negative and positive values. And also we have the constant variance. But what if we have the dependent variable? This dependent variable always takes the positive value, like we have the dependent variable, it's a price or it's an age. So in those cases, how we solve this problem? And what if our dependent variable don't have the constant variance, and this variance become larger if the value of the dependent variable become larger? And if we have the dependent variable, it's always taken two values. We use the 0 and 1 to represent the two values, like on, off, yes, no, true, false. And how about we just have the integral value, like this number of the cells? Or in auditing, we use the norm, median, high to represent risk. So it's a category variable. So when we have the independent variable is a category variable, how we solve this problem? Can we use a linear model? So the answer is that yes. So we can still use a linear model, but we need to transfer independent variable, make it ready to be used in this linear model. This we call it generalized linear regression. Generalized linear model is extension to a linear model. So it allows some nonlinear relationship to be modeled. Dependent variable is not necessary to be continuous, and the relationship between the independent variable and the dependent variable is not necessarily linear. So we can model the nonlinear relationship between the independent variable and the dependent variable. So how we do this? We try to transform the independent variable and make it ready to be used in the linear model.